section 3.3 has quite a title. 3.3 Mutually Exclusive Events and the event A, U, B. What's this U thing? You should remember this from previous chapter. This U is the union, and remember it means or, and it's the inclusive or. Remember what that means? This is like when we were talking about sets, when we were talking about set theory. If it was a union and it was the inclusive or, that means an element could belong to set A, or it could belong to set B, or it could belong to both set A and set B. That's the inclusive or. So we're going to look at that in this section. Mutually exclusive events are events that have no common outcomes. So remember when we talked about sets, those were disjoint sets when there's no elements that are in each of them. So if we're talking about probability events, that would be something like rolling an odd number and rolling an even number. Those are completely mutually exclusive, right? There's no way that you're going to roll a die and get an odd number and an even number. You can't do that. You either roll an odd one or you roll an even one. And by the way, that example I just gave you, odds and evens, those are also complementary events. Complementary events are always mutually exclusive, but not all mutually exclusive events are complementary. Ooh, how's that for confusing? For example, if you imagine flipping over a card and getting hearts, or flipping over a card and getting clubs, those are mutually exclusive. You can't turn over a card and get hearts and clubs, right? They're mutually exclusive. But those two things I just mentioned, the hearts and the clubs, those are not complementary, because there's even more things that could happen. You could flip over a card and get a diamonds, or you could flip over a card and get a spades. Okay, so think about that a little bit confusing. So let's do an example here. These are mutually exclusive events, rolling doubles or getting a sum of 7. So we're rolling 2 die, and we're looking at rolling doubles or getting the sum of 7. So let's draw a Venn diagram. Now this is a weird Venn diagram. Why is it weird? Because the circles aren't intersecting, they're not crossing. Why is this? Because these are disjoint sets. They're mutually exclusive events. This will always be what it looks like if you draw a Venn diagram for mutually exclusive events. It'll always look like this. Or if you wanted to, you certainly could draw it the normal way, like this. But what would you find in here? Nothing. There is no overlap of these two sets. So the other way we draw is like this, is disjoint sets. Okay, so rolling doubles. So let's make this one our doubles, or sum of 7. So this will be our sum of 7 one. And why don't we call it rolling doubles? We'll call that A, and sum of 7 we'll call it B. So let's list them all. Rolling doubles, well, you could get 1 and 1, you could get 2 and 2, you could get 3 and 3, you could get 4 and 4, you could get 5 and 5, or you could get 6 and 6. Do any of those add to 7? 2, 4, 6, 8, 10, 12. No, none of them add to 7. So these are mutually exclusive because there are some that add to 7, right? 1 and 6 add to 7, 2 and 5 add to 7, 3 and 4 add to 7, 4 and 3. Now I know these are kind of the same, but when you're looking at probability of dice, you have to consider the first dice getting 3 and the second one 4, or the first one getting 4 and the second one 3. 5 and 2, 6 and 1. There you go, that's all of them. Okay, now what I'd like to do is to look at the probabilities. Oh, by the way, when you roll dice, how many different possibilities are there? Well, on the first die, there's 6 possibilities, and on the second die, there's also 6 possibilities. So for a total of 6 times 6, or 36, there's a total of 36 outcomes when you roll 2 dice. So let's take a look at our probabilities. The probability of getting doubles, so that's like the probability of A, I guess. The probability of getting doubles is 1, 2, 3, 4, 5, 6. There's 6 things. 6 out of 36, right? There's 6 favorable outcomes. There's 36 total. 6 out of 36. What's the probability of getting a sum of 7? 1, 2, 3, 4, 5, 6. Oh, it's also 6 out of 36. Now, of course, you could put both of these in those terms, 1 over 6, 1 over 6. Okay, what's the probability of both of them? Okay, so this is probability of A. I should have just done like this. This is the probability of B, because I called this A, I called this B. What's the probability of A? Remember this sign? This is A and B. What's the probability of getting A and B? Well, these are mutually exclusive. For A and B, we'd be looking for an overlap here. There is no overlap, so the probability is 0. It's not going to happen. This is always going to be the case with mutually exclusive events, that the probability of getting A intersection B is going to be 0. That's what makes them mutually exclusive. But what's more interesting is this. What's the probability of A union B? So A or B. Well, we look, these are all the events that are either in this one or that one or in both. Well, there is no both, so we would just add up these ones and these ones. So that's 12 over 36, which equals 1 over 3 in lowest terms. Now, can you think of how you would get, I mean, you don't have to really think about what would you have done with these two previous answers here to get this answer? You added them together. When they're mutually exclusive and you want to get the probability of A or B, you just add together the individual probabilities. So here's two important formulas. There's this one, which is now covered, so I'll erase this so you can see it. And we actually already just wrote that. The probability of A intersecting B is 0. They don't intersect each other. There's no elements that are in both of those sets. And here's the other formula. The union of A or B, the probability of A or B, is just equal to the probability of A plus the probability of B. This is only for mutually exclusive events. So what if they're not mutually exclusive? What if they're non-mutually exclusive? First of all, what does that mean? That means they have at least one common outcome. So that would be something like rolling a sum greater than 8 or a multiple of 5. So let's draw this again, and you'll see this time I have the circles intersecting each other. That's because they're not mutually exclusive, so there is going to be some overlap. So I have my two areas here. I have sum greater than 8. I'll just put greater than 8 here, and multiple of 5, mult 5. So let's write down all the sums that are greater than 8. 1 and no, you can't do it, right? 1 and 6 is the biggest you can get, and that equals 7. 2 and 6, even that doesn't work because it has to be greater than 8. So 3 and 6 would work. 4 and 5 would work. 4 and 6 would also work. So that needs to move over into the overlap area. So I'll put that in here, the 4 and the 6. Okay, 5 and 4 will work. 5 and 5 will work. So that has to go in the middle part here, 5 and 5. 5 and 6 will work. 6 and 4 will work, and that's also a multiple of 5. 6 and 3 will work. I don't know why I didn't do that one first. And 6 and 5 will work. Okay, multiples of 5. 1 and 4 works. 2 and 3 works. 3 and 2 works. 4 and 1 will work. 4 and 6 will work, and we already have that in there. 5 and 5 will work, and we already have that in there. 6 and 4 will work, and we'll already have that in there. So I think we have them all. That was more difficult than I thought it would be. Now let's look at the probabilities. So the probability, again, let's make this A and this B. So the probability of A, again, we're rolling 2 dice, so total number of outcomes is 36 outcomes total. And if you look at A, this is this one here, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. It's 9 out of 36. I'm going to keep it not in lowest terms yet. Probability of B, that's everything in this circle. 1, 2, 3, 4, 5, 6, 7. So it's 7 out of 36. The probability of A or B. So that's A or B. Well, that means it has to be in this one, or in both of them. So in other words, we just count all these up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 out of 36. Okay, here's the interesting thing. This time we would have had a big problem if we just knew these percentages, or these probabilities, sorry, and we wanted to get this probability. Up here, all we had to do was add those. 1, 6 and 1, 6 equaled 2 6, which is a third, and that's exactly what our answer was 1/3. But down here it doesn't work. 936 plus 736 is 1636, and we want to get 1336. How could we have gotten that? Well, the key is this middle part here. How much overlap is there? 336. And I hope you see that if you took the 936, added the 736, but then took away 336, it'll give you this answer right here. Why are we taking away the 336? Because we counted it twice. We counted it once in this circle, we counted another time in this circle, so you have to subtract it once to get rid of the overlap. Okay, so your two formulas here, I mean the one's really not that useful, but it's if you're looking for the intersection of A and B, it's going to be greater than 0, of course, because that's what makes it not mutually exclusive, is that you have some overlap. So this couldn't be 0, otherwise it is mutually exclusive. But this is the very important formula. If you want to get the union of A or B, the probability of A or B, it's equal to the probability of A plus the probability of B, but that'll be too big because of the overlap, so then you subtract the probability of the overlap. Remember, this is this sign here, intersection, and it's and, so these are things, elements that are in A and B, like the pink area here is in A and B. Okay, let's try some questions. Are these events mutually exclusive? Selecting a prime number or selecting an even number? I think I already talked about this. No, these are not mutually exclusive. Which number is a prime number and also an even number? 2. Rolling the sum of 10 or rolling at least 1 2 with a pair of dice. Okay, if you've got a pair of dice and you're going to roll a sum of 10, you could do 1, 2, 3, 4 and 6, 5 and 5, or 6 and 4. That's it. If you're going to roll at least a 2 with one of the dice, that's not possible. You can't get a 2, because then in order to get a 10 you'd have to have an 8, and there's no 8 on a standard pair of dice. So yes, these are mutually exclusive. You can't have overlap here. Alright, the probability of a random student biking to school is 0.1. The probability of a student busing to school is 0.25. What's the probability of a student biking or busing to school? So the first thing you need to ask yourself is, are these mutually exclusive? And I know we could probably argue about this, but let's just be kind of reasonable about it. If someone's biking to school, are they also busing to school? I know you could say, yeah, some people throw their bike on the bus and then pick it up. Let's just assume that these are mutually exclusive, that at our school there's no one doing that. It's probably true because I don't think the number 5 bus even has a bike rack on it. So yes, these are mutually exclusive. If that's the case and you want to get the probability, the way you get the probability is you just take the probability of one event, 0.1, and add it to the other event, 0.25. There is no overlap, so you don't have to worry about that number being too big. This is your answer right there, 0.35. Pearl's about to draw a card at random from a standard deck of 52 playing cards. If she draws a face card or spade, she will win a point. Determine the probability of Pearl winning a point. So are these two things mutually exclusive? Face card and a spade. Can something be a face card and a spade? Yes, it can. So this is not mutually exclusive. So that means we have to use the other formula. Okay, so let's first of all think of what the probability is of getting a face card. So face cards, as we've said a bunch of time, are jack, queens, kings, and you have them in 4 different suits. So 3 of them times 4 equals 12. So the chances, the probability of getting a face card are 12 out of 52. There's 52 cards. What's the probability of getting a spade? There's 13 spades, so it's 13 out of 52. Now, when you want to get the overall probability, you do not just go 12 over 52 plus 13 over 52. Why not? Because there's some overlap, so you need to subtract the overlap. How much is the overlap? The overlap will be the ones that are spades and face cards. So how many spades are face cards? 3 of them. There's the jack of spades, there's the queen of spades, there's the king of spades. So there's a 3 out of 52 probability of getting a face card that's spades. So you're going to subtract that 3 over 52. 12 over 52 plus 13 over 52 is 25 over 52, minus 3 is 22 over 52, or in lowest terms, 11 over 26. The probability that Maria will go to the gym on Saturday is 0.75. The probability that she will go shopping on Saturday is 0.4. The probability that she will do neither is 0.2. Determine the probability that Maria will do both. Are these mutually exclusive? Could she go to the gym and go shopping? Yeah, for sure. This is a typical day for many teenagers, isn't it? So this is not mutually exclusive. I think this is a case where using a Venn diagram will definitely help. Personally, I really love the Venn diagrams. They help me picture a lot of these things. So let's make, I know this is terrible, but whatever. Let's make this the gym and this shopping, and let's fill in what we've got. So the probability that Maria will go to the gym is 0.75. Now I can't just put 0.75 here because that includes the whole circle. The probability that she will go shopping is 0.4. So you can't put 0.4 because that's the whole thing. We don't know how much is in the overlap area. But the probability she'll do neither is 0.2. So we can put 0.2 out here. Now if 0.2 is out here, then how much do we know there is in the whole amount here? How much is all that? Well, the whole thing has to add to 1. So we would have 1 minus 0.2 equals 0.8. So this is the probability of someone doing going to the gym or going shopping. So the union. And remember, our formula for when we have the union is the probability when we're using the union is the probability of A plus the probability of B minus the probability of A and B. This is, I guess I should have written here, A union B. And we know that amount. That amount is 0.8. We also know the probability of A. That's 0.75. The probability of someone going to the gym is 0.75. We also know the probability of B. That's 0.4, the probability of someone going shopping. What we don't know is the probability of there being overlap. So let's just call that X. And now what we have is a little algebraic equation we can solve. 0.8 equals 0.75 plus 0.4 is 1.15 minus X. Let's move the X to this side and the 0.8 to that side. So the X moves over and just becomes X. And the 0.8 comes over and becomes minus 0.8. And we get X equals 0.35. That X is the overlap area right here. And what were we looking for in this question? We wanted to know the probability that Maria would do both activities. That's exactly what that finds right in there. You found it. There's a 35% chance, 0.35. Okay, determine the odds against rolling 2 dice and getting doubles or a sum of 8. Okay, this is a tough one. So I'm going to start by drawing the Venn diagram again. Oh, are these mutually exclusive? They're not mutually exclusive. How come? Because of 4, 4. Those are doubles and a sum of 8. So I'll draw the 2 circles. And as I just said, 4, 4 is going to go in here for sure. So let's make this doubles. And this is sum of 8. So doubles 1, 1, that doesn't sum to 8. 2, 2, that doesn't sum to 8. 3, 3, that doesn't sum to 8. 4, 4 does, I put it there. 5, 5 doesn't sum to 8. 6, 6 doesn't sum to 8. So there's all my doubles with the 1 in here. The ones that sum to 8, 1 and 7, no. 2 and 6, yes. 3 and 5, 4 and 4, 5 and 3, and 6 and 2. And again, remember the total number of outcomes is 36. So let's look at the probability of getting doubles or sum of 8. So it's kind of like the probability of A or B. Okay, we could use the formula, but if you have a Venn diagram right here, it's definitely easiest just to count how many of the 36 outcomes ended up in the circles here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 out of 36, which is the same as 5 out of 18. So this is a probability, but what we're interested in is the odds against. Odds against means unfavorable outcomes compared to favorable outcomes. And what we have here is a probability where the top number is the favorable outcomes and the bottom number is the total. So I see favorable showing up in both cases, so I can put a 5 there. What's the unfavorable number of cases? Well, if the total is 18, and the favorable is 5, then the unfavorable must have been 13. So 13 to 5 are the odds against. So again, just counting made a lot of sense here. You could have done it by saying, well, the probability of getting doubles is 1, 2, 3, 4, 5, 6 out of 36. The probability of getting a sum of 8 is 1, 2, 3, 4, 5 out of 36. And the probability of having both is 1 out of 36. You add those and subtract that, you get 10 out of 36. But I mean, come on, if you've done the Venn diagram, it's not too hard just to count them up. I think it's a little bit easier.